try to understand how we're going to put these things in the water. Let's take the next panel. And we'll take the panel and we'll describe this. We'll label it as phospholipids. In water. Now remember when we describe the phosphate head group and the fatty acid side chains, that this region being hydrophobic and this region being hydrophilic imparts to this molecule its characteristic of being amphipathic. Both feeling, having an ability to interact both with an aqueous environment and a hydrophobic lipid environment. So let's think about phospholipids in water. And the first iteration of this is going to be pretty much a thought experiment. You really can't do this in the real world, but I think it's instructive to think about how phospholipids will interact with water. And so we'll again begin here simply by taking a beaker of water, imagining this is this flat surface of the water. And then up here, we're going to imagine in our mind's eye kind of salt shaker that contains phospholipids. Now mechanically you really can't do this, but I think you can imagine if we took this salt shaker full of phospholipids and we sprinkled those phospholipids out on the surface of water, that those phospholipids will now orient themselves with respect to the water in a particular fashion. And they'll orient themselves with respect to the water because the phosphate head groups are going to face the water, because after all, if this is phosphatidylcholine, these will be positively charged. That gives them the capacity now to interact with the dipole moments on water. Now there's a term that I'll use here fairly flippantly, and it's true, but you really can't grasp it until you've had some physical chemistry. And that is the lowest order state. What is the lowest order, the most probable state that we'll see here? Well, the most probable state we'll see here is for those phosphate head groups to interact with the water and turn their tails upward. So if you imagine these as little beach balls with their tails on them, the beach balls are going to face the water because the charge, the tails are going to turn away. So what you'll end up here with is with a monolayer, a single layer of phospholipids with their heads facing the water and their tails pointing upward. That really doesn't provide us with very much insight, though, into how these phospholipids are going to be functional in a biological context. Sure enough, this is the lowest order state, but what other low order states can we attain by taking these phospholipids and now imagining them not on the surface, but down amongst the water molecules? How can we put them among these water molecules? Well, the first way we're going to think about this is in something known as a micelle. So we're going to imagine taking these phospholipids and dunking them under the surface of the water. So again, the head groups are going to orient such that they point toward the water. So again, these will be the positively charged head groups. Each of these now has its two fatty acids, and they're pointing inward. So fundamentally, a micelle is a single layer of phospholipids. The head groups are pointing out to the water, and the tails are pointing inward. And this happens rarely in biology. You can get these. But in fact, this is not very stable. Because you can see is that while the head groups are interacting with the water out here, while the head groups are interacting with the dipole moments on the water, their tails are pointing inward, and we only have to get one molecule of water into this inner core where the tails are, and we're unstable, the whole thing blows up. So the problem with the micelle as a single layer of phospholipids is it's unstable. But what we can do is by employing the characteristics of the fatty acid side chains and their ability to interact in a hydrophobic environment, we can now convert this micelle into something that's far, far more stable. And the far more stable structure is said to be a liposome. What characterizes the liposome is it's a phospholipid bilayer. So again, there's going to be a kind of outer perimeter of phosphate head groups. And the phosphate head groups, being charged, will face the water. The tails, of course, will point away from the water, much like we saw in the monolayer. But what we can do to make a stable arrangement in water here is now take the tails of another layer. And point those tails inward. And now, in the middle of this, we can safely put water, because the phosphate head groups will be thermodynamically favorable. It will be thermodynamically favorable for these phosphate head groups to face water. And so we can imagine a droplet of water in the midst of this phospholipid bilayer. The outer perimeter is facing water on the outside. The inner perimeter is facing water on the inside. And we've formed, using a bilayer, a stable arrangement of phospholipids in an aqueous environment. Typically, we see these in biology, and typically the diameter of these are in terms of, they're in terms of about 20 to 400 nanometers. That's about 0.02 to 0.4 micrometers. I'll remind you that a micrometer is 1 millionth, 10 to the minus 6th meters. It's 10 to the minus 3, a thousandth of a millimeter. So tiny, tiny, well below what we can see without a light microscope, or probably an electron microscope in this case. But nonetheless, we have these individual molecules forming a bilayer. This is a sort of small sphere. And all I mean to do by pointing out these dimensions of 20 to 400 nanometers, 0.02 to 0.4 micrometers, is to say they're much, much smaller than a proper cell. A cell will typically be 10 to 20 micrometers in diameter. So 10 to 20 micrometers in diameter is like 20 times as big as this. 8 micrometers would be 20 times as big as this. So where I'm trying to emphasize here, there's a kind of spherical arrangement to this, and you can imagine it as a kind of ball. If you expand this out 10 or 20 times, then you begin to see how if you stand on the surface of the phospholipid, it's going to appear flat. It shouldn't be too much of a surprise. If we walk out of this building and look out to the horizon, it seems flat to us, yet we know that the Earth is round. It's the same orientation question as here.